All right, good morning, everybody. This is College Algebra, Math 1314. It's March the 7th. A couple of announcements to make as we head in towards spring break. Yay. WebAssign homework is, your next WebAssign homework is due on March the 18th, so that's at the end of spring break. And you have 5.4, 5.5, and 5.6, which are sections that we are either have just covered or pretty much have finished covering. As of today, we definitely will have finished covering all of them. And so make sure that you are working on WebAssign homework. Don't get behind on that. Exam 2, which covers sections 3.5, 4.1, and then all of chapter 5, 5.1 through 5.6, is after spring break. The window is March 22nd through the 27th. I did post a review for that yesterday. So you have a lengthy review. You'll be happy to know, Anne-Marie and others, that I did not list problems out of the textbook on this review. It's just all problems that I figured you'd be happy. And it's all just problems that I'm giving you, and then answers. In some cases, it's just the answer to the problem. In a lot of cases, it is the entire problem worked out. So, and in some cases, it's just partially worked out, and I'll let you fill in the details. Let's see. So that gives you something to do over spring break. Absolutely, is to start working on that exam review. On campus hours, I will be on campus the week after spring break, March 21st and 22nd. Right now, my intent is on the 21st to have office hours from 4 to 6, and then on the 22nd from 9 to 11. I put question marks there only because it's possible I could change those times. If I do, I would let everybody know, but it's conceivable I could tweak those just a little bit one way or another. But that's probably my intent right now, is those hours. And if I were to change them, I would let all of you know that I was changing them ahead of time. Cynthia and I were just talking about this a minute ago. Online office hours next week by appointment. And just send me an email or a remind message. So I'll say email or remind. Either way, I will be checking my email probably once or twice a day over spring break. So don't hesitate to, if you want to get together with me to go over something on the review or on the WebAssign homework, don't hesitate to email me and say, hey, can we set up a time where you can meet me in the WebEx room, and we'll definitely see if we can work something out. All right, and then finally, today our topic is to finish up rational functions, which we started last time, and then we're going to move into combining functions. And actually, combining functions seems like it's kind of out of the blue, but after we get through rational functions, our next goal is log and exponential functions, logarithm and exponential functions, but we have to talk about a couple of things first before we can do logarithm and exponential functions, and combining functions is one of them. Then you'll see why we need to be able to do that when we kind of get there. So we have to take a little bit of a detour. We won't get to exponential or logarithm functions before the exam, but after exam 2, that'll be the topic we start in right after exam 2. So, all right, so rational functions. Let's have a look at that. That's where we are right now. So a rational function, and you saw that with what we finished the lecture with last time, frequently have asymptotes, but we've never really necessarily talked specifically about what a rational function was. But a rational function is a fraction that is a polynomial divided by a polynomial. So they have some things in common with polynomial functions, and so that's one reason why we look at those right after polynomial functions, because they do have some things in common. But so we're talking about a fraction, but a specific kind of fraction where you have a polynomial in the numerator and a polynomial in the denominator. So there is a list of things that I want you to be able to find for a rational function. And that kind of is consistent with the way I've been doing things since we've started talking about specific kinds of functions. One way you could look at this is that with linear functions, first degree polynomial functions, I was asking you to be able to find the slope and the y-intercept and the graph. Those are things that I would want you to be able to find from a linear function. Quadratic function, I was asking you always to find the vertex. Sometimes you have to complete the square to find the vertex. The axis of symmetry. The zeros, that's when we first started talking about the word zero, and then x-intercepts and y-intercepts. You see you have this list of information that I'm going to ask you to find for these kinds of functions. With polynomial functions in general, where the degree is higher than 2, remember, linear functions is degree 1, polynomial functions, quadratic is degree 2. Polynomial functions in general, where the degree is higher than 2, again, remember there's this information that I'm going to always want you to find. So with these, I want you to find degree and leading coefficient and end behavior, right? Remember, those three things go together. And then the list of possible rational zeros. And then finally the zeros, the x-intercepts, and the y-intercept. A lot of information about a polynomial function degree greater than 2, but we've worked a lot of examples of that now in class, so you should be kind of familiar with all the things that I would be asking you for those. And so now we add on our rational functions. And with rational functions, I would want you to be able to find the vertical asymptotes. And remember, I abbreviate that VA. Horizontal asymptotes. And I abbreviate that HA like that. Now, rational functions can have a third kind of asymptote called a slant asymptote, where you have a line that's a slanted line that's a asymptote. But we don't talk about those in college algebra. That would be more of a pre-calculus topic, so we'll leave those out. And then finally, x-intercepts and y-intercepts, and then obviously again the graph. So I want to kind of fit this into the context of all the other functions that we've been talking about, in that with each of these different kinds of functions, there's some very specific information that I'm going to want you to be able to write out for that problem, for that type of problem, that type of function. And we'll continue that with exponential and logarithm functions also, where there's some certain kinds of things that I want you to be able to write out for each of those functions. All right, so our first step with rational functions is talking about vertical asymptotes. Now, a vertical asymptote is simply a place, if you think about it, where the function is not defined. Right? A typical old rational functions graph might look like this, where you have this vertical asymptote at x equals 2, for example. And so basically you're saying that the domain is everything but 2. The function is not defined at x equals 2. Right? So the function is not defined at x equals 2, because that's where the vertical asymptote is on the graph that I just sketched. In other words, f of 2 does not exist, or is undefined, either way you want to say it. Well, that kind of gives us a clue as to how to find those vertical asymptotes, right? If you have a function that's written like this, f of x equals, let's just say 3 over x minus 2. Well, what did we see there? That function is undefined at x equals 2, right? Because, so f of 2 gives you 3 over 2 minus 2, or 3 over 0. And that does not exist, or that's undefined right there. And guess what? This function has a vertical asymptote at x equals 2, right? Because that's the x value that particular function was not defined at. And where did that x minus 2, I mean, where were we worried about getting 0 here? Why is this thing undefined? And it's undefined because the denominator is equal to 0, right? And that's how you find a vertical asymptote in general. For a rational function, a vertical asymptote is an x value that makes the denominator equal to 0. And actually, there's a little bit of a condition there, and the numerator is not equal to 0. Right? You can't make both the numerator and the denominator equal to 0. We'll briefly touch on that. That's not something I'm going to look at in this class at all, where what happens when both the numerator and the denominator are 0. But you don't get a vertical asymptote in that case. So, with that in mind then, if you have this function, f of x equals x plus 6 over x plus 4, let's say, then that function has a vertical asymptote when x plus 4 is equal to 0. The denominator is equal to 0, right? And that's the key for a vertical asymptote, is you set the denominator equal to 0. Right? Those two things go together. And so what do you get? That there's a vertical asymptote at the vertical line x equals negative 4 for this particular function. Okay, easy enough. F of x equals x over 3x plus 2. So that one, the vertical asymptote, is where the denominator is equal to 0. And so you get the vertical line x equals negative 2/3. Right, that would be the vertical asymptote for that function. Again, easy enough. Everybody's disappearing on me here. And then you've got f of x equals, let's say we have 3 over x squared plus 4. Well, in this case, you take x squared plus 4, and you set it equal to 0. Now this one, you get x squared equals negative 4, and so you get x equals, when you solve that, you get plus or minus 2i, you get imaginary values, and so there's no real solutions to this equation, no real solutions here. And so this function has no vertical asymptote. Right, so just because it is a rational function doesn't mean it has to have a vertical asymptote. So this would be an example where the only place the denominator is equal to 0 is at imaginary values. There's no real numbers that make that denominator 0. All right. And then f of x equals x squared minus 2x minus 3 over x squared plus 8x plus 15. Now in that problem, that particular function, you'd want to factor, and you'll want to factor the numerator also for other reasons, but that we'll talk about in a little bit. But so the numerator factors x minus 3 times x plus 1. The denominator factors x plus 3 times x plus 5. And so for the vertical asymptotes, what are you doing here? You're setting the denominator equal to 0. And you get two vertical asymptotes in this case, don't you? Because you get x equals negative 3 and x equals negative 5. And so the vertical asymptotes in this case are the two vertical lines x equals negative 3 and x equals negative 5. Those are, so it's definitely possible to have two. In fact, a function could have any number of vertical asymptotes. Okay, so there you go. That's, and one final example here. Let's say you have x minus 2 over x squared minus 4. Now, in that case, you have x minus 2, and the denominator factor is x plus 2 times x minus 2. You are not allowed to divide out the x minus 2's there because that changes the domain of the function. So you have to leave the x minus 2's. And so what happens in this case? X equals negative 2 makes the denominator equal to 0, certainly. And so there's a vertical asymptote at x equals negative 2. But x equals positive 2 makes both the denominator equal to 0 and the numerator equal to 0. When that happens, no vertical asymptote. And like I said, that's all I'm going to do to mention that, is that there's no vertical asymptote there. There's actually what we call a hole in the graph at that point. Instead, we're just not going to talk about holes for rational functions at all. Again, that's something you would look at more in a pre-calculus class. Okay, so that's all we need to be able to do for vertical asymptotes. So now let's look at horizontal asymptotes. Now, horizontal asymptotes, if you think about those, what you're talking about there, for example, you have this horizontal line, and what happens is a graph, and maybe there's a vertical asymptote also, who knows, but the graph just gets close to the asymptote, the horizontal asymptote, as you go off to the right or as you go off to the left. Like in this case, like this. And so the graph approaches the horizontal asymptote as x gets big. That means going off to the right. Or as x gets really small, in other words, a big negative number, which means that's where you're going off to the left to do that. And what happens as you go off to the left or to the right like that, the graph gets closer and closer to this horizontal asymptote. Well, so you're specifically talking about what happens if x gets big, and bigger and bigger and bigger and bigger, right? Now notice I said big. It could be big in the positive direction or in the negative direction, either way. So positive direction or negative direction, doesn't matter. What happens when x gets big? Now, to look at that, what I want to do is to start with a function like this one right here. You have x plus 1 over 2x minus 1. Now, what I want to point out is that as x gets big, the only terms that matter, the only terms that really matter are the leading terms. Because as x gets big, think about it. In my function, I have x plus 1. Now, like let's say, Charlotte, I decide to give you $5, right? And then I decide to, let's say, take away $1. Well, you know, that makes a big difference if I give you $5. If I take away $1 from there, that's like 20% of what I gave you. And so, you know, that puts a dent in that. On the other hand, if I give you $1 million, right, which maybe you probably would be okay with that. But if I gave you $1 million and then I took away $1, who cares, right? When that big number right there, then all those smaller numbers make very little difference here. So that's what my point is with this function, is that as x gets big, as x goes to infinity, then f of x is all it's going to do is it's going to get closer and closer to x over 2x. Notice that the positive one and the negative one don't really matter as x gets big, or as x goes to negative infinity. It doesn't matter which way you go, by the way. The only terms that really control this are the first terms, the x and the 2x. And then what happens? Well, the x's would divide out in that case, and so that gets closer and closer to 1/2. And there's your horizontal asymptote. There's a horizontal asymptote at y equals 1/2, right? That horizontal line at y equals 1/2. And so the deal here is with horizontal asymptotes, the way I approach this is I look at these controlling terms, these what I call dominating terms. Those are the leading terms of the polynomials in the numerator and the denominator. And you only care about those when x is getting to be a big positive number or a big negative number. None of the other terms matter anymore. And so that would allow you to look at the horizontal asymptotes in a situation like that. All right, so let's look at some examples on the next screen of that, and let's walk through that process, that little analysis for horizontal asymptotes. So let's say we have f of x is x squared minus 2x minus 3. This is a problem I had on the screen a minute ago. X squared over x squared plus 8x plus 15. And again, so as x gets large for the horizontal asymptotes here, as x goes to either positive infinity or negative infinity, it doesn't matter, then f of x, in other words, y, right? Remember, f of x and y mean the same thing. It's going to get closer and closer to just the dominating terms of the numerator and the denominator. I'm not going to put an equal sign there. I'm going to put an arrow there, because it's not equal to these. It's just getting closer to these. So as x gets big, the minus 2x and the minus 3 in the numerator and the plus 8x and the plus 15 in the denominator, those are relatively small terms compared to the x squared terms when x is a big number. And so those other terms become insignificant, and the only significant terms as x gets large are the x squares and the x squares, right? The x squared in the numerator and the x squared in the denominator. And what happens? Well, that just approaches 1 because x squared over x squared is equal to 1. And there's your horizontal asymptote, is y equals 1. Right, so those leading terms are what you're after for the horizontal asymptotes. Let's see, so let's look at some more examples. So f of x is 3x squared minus 5x plus 6 over 5x squared minus 8x plus 10. So as x goes to positive or negative infinity, it doesn't matter which one. In this problem, f of x would approach the leading terms. We'd get, because the 3x squared and the 5x squared would be the dominating terms here. Those would be the dominating terms. And again, I want to emphasize those are the dominating terms as x gets big or small, as x goes to positive or negative infinity. They're not dominating terms if the x is a small number. Then the other terms matter. But when x gets big, the other terms don't matter anymore. So you get 3x squared over 5x squared, and that goes to 3/5. Right? And there's your horizontal asymptote. Horizontal asymptote at y equals 3/5. Okay, so it's not hard. Now, there are some situations you just need to be aware of as you go through this. So let's say we have f of x is equal to 3 over x squared minus 1. Okay? So we can still do this, even though it's just a constant in the numerator. You just have to be careful. As x goes to plus or minus infinity, in this case, f of x, well, the numerator is always 3. The numerator is a constant. And the denominator is x squared. Right, the minus 1. Excuse me. Ooh. The minus 1 doesn't matter. So now remember what x is doing. X is getting to be a bigger and bigger and bigger and bigger number, right? So what is 3 over x squared going to do as x gets to be a bigger and bigger and bigger number? Well, you think about the numerator is always 3, but the denominator just gets larger and larger. So maybe you get 3 over 10 and 3 over 100 and 3 over 1,000 and 3 over 100,000 and so on. I want you to think about that. What happens if the numerator stays 3, but the denominator just gets bigger and bigger and bigger and bigger? Well, that's just getting closer and closer to 0, right? Those fractions are getting closer and closer to 0. And so that's what happens here, is that f of x just gets closer and closer to 0 in this case, and there's a horizontal asymptote at y equals 0. And y equals 0 is simply another name for the x-axis. In other words, the x-axis is the horizontal asymptote in this case. Now, if you think about this, this is always going to happen when the degree of the numerator is less than the degree of the denominator. See, so look, let's say we have f of x is x plus 6 over x squared minus x minus 12. Okay, so as x gets to be a bigger positive or negative number, then f of x gets close to the dominating terms of the numerator and the denominator. So the dominating terms would be x and x squared. So it'd be x over x squared. One of the x's cancels and you're left with 1 over x. See, and that kind of fraction is just like the previous example. The numerator is a constant and the denominator is just getting bigger and bigger and bigger and bigger. That always will go to 0. And so the moral to the story there, and this is nice to be able to write this out all the time right away, is that if the degree of the numerator is less than the degree of the denominator, if the degree of the top is smaller than the degree of the bottom, then there's a horizontal asymptote always at y equals 0. In other words, the x-axis is always the horizontal asymptote. That is a nice little rule to know about a rational function, that if the degree of the numerator is less than the degree of the denominator, then there's always a horizontal asymptote on the x-axis. Sometimes you'll see instructors refer to these as bottom-heavy rational functions because the degree of the bottom is bigger than the degree of the top, right? And so if you know that going into a problem, then you can just write down the horizontal asymptotes at y equals 0 and you can be done with it. Now notice that didn't apply to the two problems at the very top of the screen, because at the top of the screen those are both degree 2 polynomials. So the degree of the numerator and the denominator were the same on those problems. So, all right, and so now that's where the degree at the bottom is the degree of the numerator is less than the degree of the denominator. So let's look at it the other way. Let's say that the degree of the numerator is the bigger one. These would be top-heavy rational functions. So let's say we have x cubed minus 1 over x squared plus 16. Right here, notice the degree of the numerator is bigger than the degree of the denominator. So we don't do anything different from what we've been talking about. We examine the leading terms, the dominating terms. So as f of x gets closer or gets bigger and bigger or smaller and smaller, as it goes to positive infinity or negative infinity, then f of x in this problem, in this particular function, would get closer to x cubed over x squared. Right? The minus 1 and the plus 16 don't matter as x gets to be a big number or a small number. Well, and then what happens there? Well, the x's cancel and you're left with x over 1. But what's happening? X is getting to be a bigger and bigger number. And see, so that just goes to infinity. And so in this case, there's no horizontal asymptote. right? Because the f of x value, the y value, just goes to either positive infinity or negative infinity, depending on whether x is positive or negative. So I'll put plus or minus infinity there because it could go to negative infinity also. And so the moral to the story here is that if the degree of the numerator is bigger than the degree of the denominator, right? If the degree of the numerator is bigger than the degree of the denominator, this is sometimes called a top-heavy function, then what happens? No horizontal asymptote. And in fact, let's go ahead and put those rules so that they're on the same screen here. So if the numerator degree is bigger than the denominator, no horizontal asymptote. If the degree of the numerator is less than the degree of the denominator, sometimes called a bottom-heavy rational function, then there's a horizontal asymptote, in this case, at y equals 0, in other words, the x-axis. And then finally, the degree of the numerator is equal to the degree of the denominator. Those are the first groups of problems we were looking at. When the degrees of the top and the bottom are the same, then what are you going to look at? You're going to look at the dominating terms in the numerator and the denominator. So look at dominating terms of numerator and denominator. All right, and so we've been talking about how to do that. So this is a nice little summary of how to deal with horizontal asymptotes right there. All right, so now we've got the asymptotes taken care of. Vertical asymptotes, horizontal asymptotes. The next thing we need to do is look at the intercepts, the x-intercepts and the y-intercepts. So the only one that we really need to kind of pay attention to are the x-intercepts. So let's say we have this function f of x equals 2x plus 1 over x minus 3. And we want to find the x-intercepts. Well, we know that to find any x-intercepts, you simply set y equal to 0. So I set y, remember, f of x and y mean the same thing. So I set f of x equals 0. And I get that equation right there, 0 equals 2x plus 1 over x minus 3. Well, and then to solve that equation, that's a fraction equals 0. You get rid of the fractions. So you just multiply everything by x minus 3. And when you multiply by x minus 3, on both sides you get 0 equals 2x plus 1. You cleared out the fractions. And what I want to point out here is, what did you end up with? You ended up with the numerator equals 0. And see, that will always happen. This will always happen when you're looking at x-intercepts. Is you're always just going to end up with the numerator being equal to 0. And then you just solve for x. So in this case, I get x equals negative 1/2. And so this function has an x-intercept at x equals negative 1/2. Well, so let's go ahead and put it as a point at negative 1/2 0. Right, so the moral to the story here, x-intercepts set the numerator equal to 0. And let's go ahead and put next to this, remember that vertical asymptotes, what do? You set the denominator equal to 0, right? Because vertical asymptotes are where the function is undefined. And so it's good to have those two things sitting right next to each other to make sure you distinguish, right? How does a fraction get to be equal to 0? A fraction gets to be 0 if the top is 0. How is a fraction undefined? It's undefined if the bottom is 0. That's what we're talking about here. All right, so let me put a box around those two things. And finally, the y-intercepts. The y-intercepts really are kind of trivial in a lot of ways because we know to find y-intercepts, you simply set x equals 0. So like in the problem I just looked at, you're looking at f of 0. Right? That's setting x equal to 0. So you just simply substitute 0 every place you see an x, and you do the calculation. So the y-intercept's at 0, negative 1/3. And so I'll go ahead and put a box around that. For y-intercept, set x equals 0. In other words, calculate f of 0. All right, that's what you're looking at. All right, so now what we want to do is kind of put all this stuff together and look at some problems where we go through everything on a rational function, and then we actually sketch the graph of the function. Make a rough sketch of the graph. And you can use your calculator to help you with this graph also. F of x equals, let's say we have 2x minus 1 over x plus 1. All right, 2x minus 1 over x plus 1. So we're going to go through all the different things we've just talked about and try to piece them together and look at the graph. So the first thing is the vertical asymptote. And the vertical asymptote in this problem, remember how you find it, is you set the denominator equal to 0. So that's x plus 1 equals 0, or x equals negative 1. So there's a vertical asymptote at x equals negative 1. The horizontal asymptote. You look at the dominating terms as x gets big. And as x gets big, as x goes to infinity, f of x goes to 2x over x, right? Those are the dominating terms in this function, or 2, right? Because the x's would divide out. And so you have a horizontal asymptote at y equals 2. The x-intercept, or intercepts, depending on the problem. There you set the numerator equal to 0. And so if I set the numerator equal to 0, I get 2x minus 1 equals 0. Add 1 and divide by 2, and you get x equals 1/2. And so there's an x-intercept at 1/2, 0. All right, and then finally the y-intercept for the function. Remember, a rational function, any function, can only have one y-intercept at the most. Otherwise, it would fail the vertical line test. The y-intercept, we look at f of 0. We plug 0 in for x. So you have 2 times 0 minus 1 over 0 plus 1. And so you get negative 1. And so there's a y-intercept at 0, negative 1. All right, so now let's kind of piece this together and let's see what we can come up with on the graph. And what I'm going to do, you can certainly use your graphing calculator to help you with the graph. I'm going to just kind of try to use the information I've given and maybe plot a few extra points to find a decent sketch of the graph. I'm going to do it kind of the old-fashioned way here. All right, so let's put in all the information. There's a horizontal asymptote at y equals 2. I put a dotted line on the horizontal line y equals 2. Vertical asymptote at x equals negative 1. So I put a dash line there at x equals negative 1. And then I go ahead and sketch put in the intercepts. There's an intercept at positive 1/2, 0. That's an x-intercept. And there's a y-intercept at 0, negative 1 right there. So those are my two intercepts. Now, what I want you to think about here is that a rational function, the graph has branches. For rational functions, the graph has branches. And the vertical asymptotes tell you how many branches there are, right? In this case, there's one vertical asymptote, so there must be a branch. A branch is on either side of the vertical asymptote. So there is a branch on either side of the asymptote. So this graph has two branches. And when I say asymptote there, I'm talking about the vertical asymptote. This graph has two branches, one branch to the left and one branch to the right of the vertical asymptote. Now, let's look at the branches. For the branch on the right side, by the way, a graph can never ever cross a vertical asymptote. So rational functions never, ever cross vertical asymptotes. Rational functions can, believe it or not, can cross horizontal asymptotes. And I'll show you how that occurs as we get into this. But for problems like this, they're not going to cross the horizontal asymptotes, but there are other kinds of rational functions where they can, and we'll talk about that in a minute. All right, so I want you to look at the branch on the right side of the asymptote. The branch on the right side of the asymptote could either, let's put this in pink here. I'm going to put this as a dashed line. It could either go like this and fit in between the two, the vertical and the horizontal asymptote like that, or it can go like this and cross like that. Those are the two possibilities for the branches to the right of the asymptote. And by the way, that's the same as the branches to the left. They either could go like this or go like that. Right? So you're trying to decide which one of those they are. It can't be both of them on either side, because remember, the graph must pass the vertical line test, right? Because they are functions, right? This graph must pass the vertical line test. So don't draw anything that doesn't pass the vertical line test. Well, if you look at it, those two asymptotes, or those two intercepts that I plotted, tell you where that branch to the right has to be. The branch to the right has got to look like this. Right? It's got to be to the down below because of those two intercepts like that. And so there's no question that's got to be the branch to the right of the vertical asymptote. Now the branch, you actually do have enough information to find the branch to the left and where it is. But if you're not sure where it is, then the idea here would be to plot a few points, a few appropriate points that would tell you where this branch has got to be. So for example, I could pick x equals -2, and maybe even x equals -3, like that. And I could calculate those values. I could look at f of -2 and f of -3 and plot those points. So f of -2, if you plug -2 into the original function, right, you get that calculation there, and you get -5 over -1, or +5. So that means at -2, this graph is up here at 5, right, at the point 2,5, -2,5. And so that starts giving you a good idea where this other branch has got to be. Now, if you still want more evidence, look at f of -3. F of -3 would be 2 times -3 minus 1 over -3 plus 1. And so that'd be -7 over -2, or 7/2, just 3.5. Right about there. Right, and so that's giving you a really good idea where this other branch has got to fit in. The other branch has got to fit in like this, right? And there's your graph, right? And so think about where those branches have got to be, how many branches there are for a rational function. Don't forget that you can use your graphing calculator here. The only thing I would be warning you about on a graphing calculator is I see students enter this incorrectly all the time. On a graphing calculator, enter it like this. Make sure you use parentheses. So you enter it as y equals, and you put parentheses around the numerator, divided by, and then parentheses around the denominator like that. Don't enter this. Don't enter just y equals 2x minus 1 divided by x plus 1. That is not the same function right there. Right, so you have to make sure that you enter parentheses correctly. All right, so let's look at another example. So I'd expect you to stop me if you have a question, by the way. So don't hesitate to stop me if you've got a question. And, this is a lot to piece together on a problem. I understand that. But I'm not going to, by the way, I'm not going to go crazy with how difficult these problems are going to be, just so you know. So hopefully that'll make you feel a little bit better. So let's say we have f of x equals x minus 2 over, excuse me, let's say I've got x squared minus 2x minus 24. There we go. All right, so the first thing that you always want to do in a problem like this is you always want to do any factoring you can. So this is x minus 2 over x minus 6 times x plus 4. Always do all the factoring that you can in the problem. All right, so the vertical asymptotes. So the vertical asymptotes, remember, is where the denominator is equal to 0. And the vertical asymptote then would be at x equals 6 and at x equals negative 4. Right, those are the vertical asymptotes. So there's two of them. Horizontal asymptote. This is an example of a bottom-heavy function, right? The degree of the bottom is bigger than the degree of the top. And so since it's a bottom-heavy function, since the degree of the denominator is bigger than the degree of the numerator, we talked about the fact that the horizontal asymptote is at y equals 0, or the x-axis. Right, that will always be true. All right, the x-intercepts. The x-intercept, remember, is where the numerator is equal to 0, because the fraction has got to be equal to 0. And so that would be where x minus 2 is equal to 0. There's an x-intercept at 2, 0. And notice, because there's an x-intercept, and because the x-axis is the horizontal asymptote, notice that the horizontal asymptote is crossed at the x-intercept here. So the horizontal asymptote is crossed at x equals 2. Right. So this would be an example of the horizontal asymptote being crossed in a rational function. And then finally the y-intercept. We simply look at f of 0. So f of 0 in our go to the original function to do this. This is 0 minus 2 over 0 squared minus 2 times 0 minus 24. And so this is going to be 1 over 12, positive 1/12. And so there's a y-intercept, not a very big number, right? It's just 0, 1/12. All right, so let's go ahead and put this stuff together on the graph now. And maybe we'll plot a few extra points if we need them. All right, so let's see. I have a vertical asymptote. Let's look at the vertical asymptotes. There's one at 6. 1, 2, 3, 4, 5, 6. So here's our vertical asymptote. And another one at negative 4. So here's a vertical asymptote at negative 4. Now, because there are 2 vertical asymptotes, this graph has 3 branches. Right, it has 3 branches. Whoops. Remember that those vertical asymptotes tell you how many branches you've got. So there's a branch to the left, there's a branch in between, and there's a branch to the right. Right, so there's branch 1 is over here. Branch 2 is between. And then branch 3 is over here to the right. There is a horizontal asymptote on the x-axis. I'm going to put this dashed line just a little tiny bit above so we can actually see it. But there's a horizontal asymptote sitting right there. And then we have a x-intercept at 2, 0. and a y-intercept just barely above the x-axis at 1/12, like that. All right, so maybe let's focus, since the two intercepts are sitting there in the middle. Put those maybe in green. Since those two intercepts are on that middle branch, branch 2, let's go ahead and concentrate on branch 2, and let's do some other calculations here for some other y values. So let's pick something pretty close to the asymptote. So f of 5, because that's pretty close to that vertical asymptote at x equals 6. So f of 5, I'm going to look at the factored version. So I get 5 minus 2 over 5 minus 6 times 5 plus 4. That's not a bad form to look at. And so f of 5 is equal to 3 over negative 1 times 9, and that's negative 1/3. Gee. So negative 1/3 is right here maybe, but it's not very far down. And then let's look at f of negative 3. So f of negative 3 in the numerator would be negative 5, and in the denominator would be negative 9 times 1. And so you get positive 5 9ths. A little bit past a half, so maybe like right there. And so those points are giving you an idea of what that middle branch has got to be like. The branch, remember, has got to get close to these vertical asymptotes. So this branch has got to come in like this. And then evidently it's very flat right in here, right? The intercepts are pretty darn close together. And then the graph comes down towards this asymptote like this. So it's pretty tight shape in there in between those asymptotes. And notice it actually crossed the horizontal asymptote in the middle there. Now the branches on the outside, you could plot more points if you wanted to figure out where that graph was. So like I might look at f of 8. Let's see where the graph is when x is 8. F of 8, in the numerator you get 6, and in the denominator I get 2 times 12. So you get 6 over 24, or 1/4. So at 8, gee, the graph's really low down, but it's above the x-axis. And so that tells you that this branch has got to sit above this horizontal asymptote. It can't cross the asymptote anywhere else. We've already found that point, and so that asymptote's fitting pretty tightly in up there. And then maybe find f of negative 5. Negative 5 is way off to the left. And actually, let's look at negative 6. Go a little bit further past that asymptote. So f of negative 6 would be negative 8 in the numerator, and then negative 12 times negative 2 in the denominator. So you get negative 8 over 24, or negative 1/3. So at negative 6, the graph is pretty tightly in right in there, right below the x-axis. And so that branch, that tells you that branch has got to fit in like that. And so you've got a decent sketch of the graph. You know, and all I'm going to be looking for here is rough sketches. And again, don't forget that you can use your graphing calculator to kind of help you with where this sets up like this. So, all right, so that's another rational function there. All right, let's kind of finish this discussion. I still want to look at some combining function stuff to finish class today, and we have enough time for that. Let's look at a problem like this one, and all I'm going to do here is find all the information. We are not going to worry about the graph on this one. There will be problems where I just ask you to find a lot of information, but not to worry about the graphs at all. So let's say we have f of x is x squared minus 2x minus 3 over x squared minus 16. All right, so remember what I asked you to do here at the beginning in a problem like this is any factoring, go ahead and do that. So you have x minus 3 times x plus 1 in the numerator. And then in the denominator, that's the difference of squares. That factors x plus 4 times x minus 4. All right, so the vertical asymptotes. Remember, the vertical asymptotes is where the denominator is equal to 0. And so the denominator is equal to 0 at -4 and at +4. And if we are looking at the graph on this one, the graph has 3 branches again, right, because of those 2 vertical asymptotes. The horizontal asymptote, right, we look at the dominating terms in the numerator and the denominator. And so the dominating terms are the x squared terms. So this goes to x squared over x squared, right? You don't care about the other terms as x gets big. And so the horizontal asymptote's at 1. So you have a horizontal asymptote at y equals 1. X-intercepts. We look at where the numerator is equal to 0. Remember, that's where the fraction is equal to 0, and that's the numerator. And so the numerator is 0 when x is 3, so you have 3, 0. And also at -1, you have -1, 0. Finally, the y-intercept. We calculate f of 0 to find the y-intercept. And so that would be 0 squared minus 2 times 0 minus 3 over 0 squared minus 16. And so the y-intercept's at 3/16. And so let me put that as a point. So that'd be 0, 3/16, like that. All right, and let's actually look at this, this problem on my app, and let's actually talk about the graph and how all this stuff fits in. So let's go ahead and enter this. That's something I was looking at in Cal 2 the other day. So let's see. So you've got x squared minus 2x minus 3. So if you look at how I'm entering this function on your screen here, just like in a graphing calculator, I've got to do the same thing. Notice I put parentheses around the entire numerator, and I put parentheses around the entire denominator. Make sure that you do that. All right, and so let's go ahead and sketch the graph here. And there's the graph of this particular function. And so notice that, and actually let me go ahead and import this graph into my here we go. And we'll go ahead and talk about this graph here. All right, so notice that the asymptotes here, that there's an asymptote. I made the graph kind of small, but there's an asymptote certainly here at -4 and another one here at +4. It really fits in tightly in there, so it's hard to see at this point, but you've got one at -4 and +4. You have a horizontal asymptote at y equals 1, and you can kind of see it on my graph in there. Now, it looks like the graph's crossing. It's only because I've zoomed back so much. That's the only reason why. And then you have intercepts, and sure enough, the intercepts fit in like they're supposed to. Right, you have an intercept here at 3, 0, and another one at -1, 0. Notice this middle branch is really different than the last middle branch. This one stays on the same side of the horizontal asymptote, like that. And then finally, there's a y-intercept at 3/16, and you can kind of sort of see that on the graph also. So you can kind of, and you could plot points to get a good idea that this was actually the right sketch of the graph here. So that fits in pretty well. So use your graphing calculator in the same way. Sketch the graph on your calculator and can kind of compare the two and see if you're getting the graph, fitting the math that you're writing out, the algebra that you're writing out in the problem. All right, so that's our example. So the last 10 or 15 minutes of class here. So we have still about 10 or 15 minutes that I want to take to finish up class today. What we're going to do, we've now finished rational functions. Right? We started rational functions last time by looking at graphs of rational functions and getting information from those graphs. There is at least one or two problems on your review, like what we did in lecture on Monday on rational functions. And then there's several like what we've done today. They're not going to be real difficult, but just a few basic rational functions to look at. So we've finished rational functions. We've finished chapter 5. So our next goal for class, our next goal is going to be to talk about exponential functions, and logarithm functions. Now the question is, what the heck is a rational function or an exponential function or a logarithm function? We are not ready to talk about that yet. And then the other question is, why are exponential and logarithm functions always talked about at the same time? Once again, we're not ready to talk about that. What we have to do is we have to take a detour first. And the detour is we're going to actually go back to section 3.7, and 3.7 is discussing what it means for two functions to be inverses of each other, inverse functions. So you've got to talk about inverse functions before you talk about exponential and logarithm functions. Why? Well, because it turns out exponential and logarithm functions are inverses of each other. So in order to understand what you're doing with exponential and logarithm functions, you got to know something about inverse functions. And so that's a detour. And then, well, inverse functions, in order to understand those, you have to talk about composition and or function composition. And function composition is an example of what we call combining functions. So what you have to do first is you have to go back and deal with composition first, or combining functions. Go all the way back to section 3.4, and then talk about inverse functions, and then you can talk about exponential and logarithm functions. And so that's what we're going to do, is we're going to go back to section 3.4 and talk about combining functions, and then that will allow us to talk about inverses and then exponential and logarithm functions. Now the combining function stuff is not too bad, and I really wanted to talk about this before spring break, so that we could kind of sort of keep on our calendar. And so we're going to look at combining functions here in a simple example. And then after we've talked about combining functions, then we can shut it down for spring break, and then we'll come back and we'll talk about inverse functions. Now, so when we're talking about combining functions, look, I'm just going to give you, we're going to start with two functions. F of x is 2x plus 1, and g of x equals x squared minus 4. All right, so combining functions, basically there's 5 ways to do this. And the first 4 are pretty obvious. The first 4 are just, you add the two functions together. And the function's name is f plus g of x. And it's literally just means taking the two functions and adding them. It's all it is. Nothing mysterious about it. So it's literally 2x plus 1 plus x squared minus 4. And so f plus g of x, you just combine like terms as x squared plus 2x minus 3. That's all it is. You just add them together. F minus g, so now I bet you know how to do f minus g. All right, that was just to take the two functions and subtract them. Here you just have to be careful that you don't make a sign mistake. But other than that, it's simply combining like terms and subtraction. So f minus g of x, let's see, let's get the terms right here. So this would be negative x squared, and then positive 2x. And then you have 1 minus negative 4, so that's 1 plus 4, or 5. So you see, this is not hard at all. And then you have the multiplication function. This would be, sometimes is written just fg of x. Sometimes written f dot to g, sometimes just written fg of x. And that's simply take the two functions and multiply them together. So it's f of x times g of x. So this would be just 2x plus 1, times x squared minus 4. And that would be the FOIL method, right? You just multiply them together using the FOIL method. This would be 2x cubed plus x squared minus 8x minus 4. And that would be fg of x. And so fg of x would be equal to 2x cubed plus x squared minus 8x minus 4, like that. All right, and so this is not hard. Let me copy those two functions down, carry them over to the next page, and then just another couple of examples here, and then we'll be finished for the day. So f over g of x, that's the division function. And so that just says take f of x and divide it by g of x. And so that would be literally just 2x plus 1 over x squared minus 4. And so that's f over g of x. Now, f over g of x does have some restrictions on the domain that the other functions don't. The other functions are all polynomials, and so no restrictions on their domains, and the domains on all those are all reals. For this last one, because the denominator is 0 at negative 2 and 2, those are vertical asymptotes. Those are also restrictions on the domain, right? That x cannot be equal to negative 2 and x cannot be equal to 2, right? There's vertical asymptotes at those values, like we just talked about at x equals negative 2 and x equals 2. All right, I'm not going to make a big deal about the domains. There's a couple of questions on WebAssign where they talk about the domains, and we'll talk more about that after spring break a little bit. But I'm not going to make a big deal about it. The last way to take these two functions and combine them is called function composition. Function composition, or just composition. And function composition in words is simply talking about a function of a function. In other words, you literally plug one of the functions into the other one. So, for example, we might have, and the notation looks like this. It's actually written with a circle between the two functions. That's the notation for composition. F circle g of x. And that's really f of g of x. That's really what that means. And so I would write that definition out right away. And this is the f function of the g function, right? The g function, you start with the inside one, is x squared minus 4. So this is really f of x squared minus 4. And what you're doing is you're literally going to the function f. Here's the function f right here. Remember that f of x is 2x plus 1. And so in place of the x, you dropping in x squared minus 4. So you're literally dropping the g function into the f function. You're substituting the g function into the f function. So substitute the g function into the f function. And so notice that's what I did. I plugged x squared minus 4 into 2x plus 1. And then you just do the arithmetic there, and you get 2x squared minus 8 plus 1, or 2x squared minus 7. And that's f circle g of x. Right, it's the function 2x squared minus 7. Now we're going to talk more about what that actually means after spring break. But what I want you to be able to do right now is just form that function. Now you could do this the other direction too. You could do g circle f of x as well. And all you're doing is the opposite in this case. So this is g of f of x. And so what you're doing here is you are substituting the f function into the g function. So the g function is x squared minus, well, first of all, so that's g of 2x plus 1. And so what do? You go to the function g, you write it down, but in place of an x, you put 2x plus 1. You drop the 2x plus 1 into that function. And so you get 2x plus 1 squared minus 4. And then again, it's just a matter of doing the arithmetic. So function composition has to do with substituting one function into the other function. Right? One of them, you substitute g function into the f function. Right? When do you do that? You do that for this one, f circle g of x. That's defined to be f of g of x. And then the other composition, the other direction, you substitute the f function into the g function. Right? And that's g circle f of x, or g of f of x, like that. All right, and then let's see. This would be 4x squared plus 4x plus 1 minus 4, or 4x squared plus 4x minus 3. Now, as you get a completely different function here, that would be typically the case. And that would be g circle f of x right there, is that one right there. So I wanted to kind of walk through composition in particular, because I want you to see that before spring break. We will talk a little bit more about combining functions after spring break is over. And then, but then we'll move into talking about inverse functions after spring break. And remember, the week after spring break, so let's go to the next screen here. The week after spring break, and this is all on your calendar now, but I wanted to kind of highlight this again. And so that's the first day after spring break is March 19th, and we have a lecture. And I'm going to lecture on section 3.7 on inverse functions. And then on 321, no lecture on that day, right? Because what am I going to be? I'm going to be on campus that day. So I'll be on campus instead. And then the following week, once again, no lecture on 326. Right, so 326, no lecture again, because that's during the testing window. And then finally, on March 28th, we'll start lecturing again. Right, so now, between now, so today's March the 7th and March the 28th, we only have one lecture that I'm going to be posting up during that time period. So, but you'll be hearing from me on Remind, definitely. So don't hesitate to get in touch with me. Please don't hesitate to get in touch with me if you have questions, if you want to meet with me over spring break in my WebEx room. I definitely have no problems with you doing that. All right, and then finally, if you want textbook practice, I always try to put this in here. I don't know if anybody works this or not, but this is good textbook practice. This is page 431 on rational functions, 11, 13, 15, 19, 21, 23, and then 39, 41, and 43. Don't forget the exam to review also. That's important, definitely. All right, Charlotte and Justin, you guys are the only ones that survived the entire